Hello and welcome to class problem chapter 14. So these are the class problems for chapter 14 here. I have some of this stuff already kind of preloaded to cut down on the time of the video, but I'll still try to get as much information as I can to you. So I've circled the correct answers for the first page here, and for ones that I thought that where most people may have missed something, I've indicated the page number in which you can find more information for in the book. So like number 2, which the following is not a formal condition for inference about a regression estimate, and it's heteroscedasticity between x and y variables. Question number 3, anytime we're dealing with r squared, you're going to want to think of variation or the variance. Remember, if you have standard deviation as your s, and then s squared is your variance or the variation, so think r squared is the variance, so that's why I underline variation there in the frequency for you. When you have no linear correlation, the answer is 0. You want the population slope beta, not b. You can find that on page 356. When we're talking about central limit theorem, when it comes to the application of the correlation, it is not applied, therefore this is false. And you can find that on page 346. We do use correlation coefficient rho when dealing with hypothesis statement, so that's true. And the open answer, when we deal with R and strength of association, remember R is going to be looked at as an absolute value, and absolute value of negative 0.59 is a stronger association than positive 0.4 absolute value. So that's how you answer that one. So this next part here, suppose the following table represents a simple random sample of hospitals enrolled in a study looking at the relationship between number of beds and number of physicians working full-time at the facility. So right here in the very top part, you have the number of beds and then the number of physicians full-time. I have told you what your x and y variables are. However, for correlation, doesn't matter what your x and y variables are. The only time this comes into consideration is when we're doing linear regression. And most of the time I've stated it for you, but just keep an eye on that throughout the packet, because I do switch it up on you. And then we want to figure out a correlation between the two. So part A is calculate a base of descriptive statistics for both your x and y variables. So you want to find your mean and standard deviations. And then we're going to calculate the correlation coefficient. So what I've kind of done is created a little chart here in Excel, in which you'll see the number of beds, which is the same as up here, and the values there. Same with the number of physicians and the values associated here. And here they're the same. And on the side here, I've given you what your x bar is and y bar. Can't do that in Excel. And then the standard deviation of x, standard deviation of y, and the values that they equal to. And so I've kind of set this up to help show the steps in the process to calculating an R value. So what you do is you would take the number of beds, so 589, and you subtract it from your x bar. So that's what this is stating up here, x minus x bar. So you take number of beds, subtract it from your x bar, which is found here, and then you get this value. Once you get this value, divide it by the standard deviation of x here, and then you'll get this value, 0.686546. You only have to go for decimal spots out. You don't have to do more. Since I did this in Excel, I have Excel to go up many decimal points, and I didn't change it. So don't worry about going all the way out. 4 is fine. And then you do the same thing for the physicians. So physicians, as you can see, some of these cells are blank, and this is where you fill in the points, and this is the slow start up to the whole packet, where we get you started off slow, and then we get you into it so you can see the steps, kind of baby steps through it, and then we get to the full problems. So you take 948 minus your y bar, which is 851.4286, and you'll get a value of 96.5715, and then you take the 96.5715 and you divide by the standard deviation of y, which is 150.853, and when you divide it out, you'll get a value of 0.64 0.017. And then for right now, we're just going to keep finishing the table. So you take your value of number of beds and subtract it from your x bar. So 517 minus your x bar of 511.28, and you would get 5.7143. Divide by the standard deviation of x, and you get 0.05048. So now you can see the steps. Each one of these steps is you take the value in the column, minus it from the y bar, x bar, the average, and then divide by standard deviation of x, and that gives you your, this column here will be your z of x, and this column here is going to be your z of y. And then we'll multiply them out. So finish the table out. So I'm going to do that real quick. So this is 0.00631. This one we're taking 846, minusing our y bar. You get negative 5.4285. Divide by standard deviation, negative 0.03599. Continuing on, 85.7143. So as you can see, these steps aren't anything mind-shattering. You know, the steps are here, they're laid out for you, and it's not that much. The part that makes this a little easier is that you are given the x bar and y bar and standard deviations for both, and once you have that certainly makes this a lot faster of a problem to accomplish. If you didn't have that, then you would have to do a lot more work, because you would have to find your x bar and standard deviations for each of these data sets. So now we have our table filled in. We want to find our zx, zy, and the way we do it is we take our values found in this column and we match it up to the values in the other column, and we multiply them out. So we would take 0.6865 times 0.64017, and when you multiply those out, you'll get 0.4395. Same thing for the bottom. You just take the value that you got for your s of x, multiply it by that value of your s of y, and you get 0.0266. You keep doing that all the way across, multiplying your s of x times your s of y, your z of x times your z of y, excuse me, and I'll finish filling in your chart here. And it's 2.1222.6805, and then 0.8594. Cells are kind of small, so I'm trying my best to get all the values in there. And then when you have your z of x, z of y, we're going to stop there just for a second, because I'm going to go down to part B, which is calculating the correlation coefficient, or the Pearson's R. And in order to calculate your R value, you take 1 over n minus 1 times the sum of z, x, z, y. So it's the sum of zx times zy. So that's what you did here. So here's zx, zy, and then right here all we have to do is add them all up. And this, when you add these up, you get 5.6701. And now this is your sum. When you add them all up, that's your sum, so that's your sigma. So now we have all our values that we need. Our n is going to equal 7. We have 7 different data points here. 5, 6, 7. And so we have 1 over 7 minus 1 times the sum of zx, zy, which is 5.60, I'm sorry, jumping ahead here, 5.6701. And then you take 7 minus 1, so it's be 1 over 6. 1 over 6 is 0.1667, and you're going to multiply that times 5.6701. And when you multiply those out, you'll get a R value of 0.945. Okay, so that equals R. Highly recommend always, when you get an answer, know what you're equaling to, right? We started with R equaling, and this is what we equal. So we equal with 0.945. And then how would we describe this? How would we describe this value here? Well, we'd say this is a strong positive association. And when we look at R values in the book, there's a section, it's on page, let me look it up for you all real quick, 338, and when you take the absolute value of R, it gives you the strength of association. Anything above 0.7 is going to be a strong association. We're dictating the slope of it by saying it's positive, so we know it's a positive association. So if we had a correlation, we know it's going to be going sloping up, so it's a positive association. This is your X and Y. And so a 0.945 R value is a strong positive association. Next part is we're going to write out our null and alternative hypothesis for formal hypothesis testing with the number of beds to position. So anytime we're doing hypothesis testing, you're going to say our null hypothesis, and we're going to be using the value of rho, which looks like a p, but it's not, it's rho, is equal to 0, right? We're stating that there's no difference between these 2 points, these two sets here, and an alternative hypothesis is going to state that rho does not equal 0, the two-tail hypothesis test. In order to calculate our t-statistic, we take our t-stat. It's going to equal R over standard error of R, where the standard error of R is equal to the square root of 1 minus R squared over n minus 2. And our degrees of freedom is equal to n minus 2 when we're dealing with correlation. So we have all the values we need to do our t-stat. We take 1 minus 0.945 squared, right? That is our R value. And we divide it over our n, which is 7 minus 2. We're going to take the square root of all that. When we simplify this out, when you square, then subtract, then divide, and take the square root, you will get 0.1463. And remember, that is equal to our standard error of R. So we just calculated the denominator here. So now we take 0.945 divided by 0.1463, right? Because this is our R divided by the standard error of R. And then we get a value, of 6.459, and this is equal to the t-stat. And so when you go to the back of the book and you go to table C, and that's our t-table, when you go there, you'll look up alpha level 0.05 with the degrees of freedom 5, two-tail test, and we'll see that our t-crit value, so at what value does t become critical or significant at alpha level 0.05, and our t-critical value is going to equal 2.571. Our t-stat is greater than that, so we show significance there against the null hypothesis. The true p-value, if you go down further and further, you'll notice that our p-value will be between 0.002, so it'll be less than 0.002, but greater than 0.001, and the true p-value for this would be 0.0013, which makes sense, it falls in between here. And that's all we say. So on the test, we would say where it's critical at for there. There wasn't an alpha level given, so we would always assume that it's 0.05. And then if we want to be more specific, we would say it falls between these values on the t-table. Okay, so I'm not sure how much time I have left. I don't think I have much more time.